we've seen that the system is more or less linear, not exactly so, in the sense there is an envelope within which the system might be linear. And so if that is the case, how can we tease apart overlapping trials? How can we tell if they're two contiguous trials, but where the bold response overlaps? How can we tell from that overlap how much of it is due to trial A and how much of it is due to the second trial? Now, there are two ways that allow us to tease apart the variance due to two contiguous trials. Now, the first way in which we do that is by shuffling the order of trials, which simply means when you're presenting your A and B task, you want to shuffle them sufficiently. Now, this is important for at least two reasons. There's a statistical reason, which means that in order for us to calculate how much of the effect comes from one condition, let's say condition A, and how much comes from a condition B, we need to have enough shuffling so that we avoid something called multi-collinearity. We avoid the circumstance where there's a relationship between when trial A occurs and when trial B occurs. But we're gonna go into this detail later on when we talk about statistical analysis of fMRI time series. At this time, the more important aspect is the psychological aspect. Because see, if you imagine that there's something in your experimental design, there's something in the shuffling that is not fully well done, maybe your participant might detect that. And if they detect that there's some kind of systematicity to when trial A, when condition A or condition B is appearing, they might be able to leverage that to create expectations, to create cognitive strategies, which is what we're trying to avoid. So it's very important to shuffle as much as possible the presentation of trial type A and trial type B if you're using an event-related design. Now, in order to actually implement this, the way in which people started doing this is known as counterbalancing. Now, counterbalancing means shuffling in a systematic way the trials so that they're perfectly counterbalanced. Now, this is great, but it's hard to implement in practice. Let me show you what I mean. Say we have two conditions, condition A and condition B. So for starters, obviously, we want the trials to be 50-50 so that the participant cannot, for example, notice that, oh, 70% of the times it is condition B versus condition A, because that would allow them to develop some kind of systematic approach to your task, which again is what we're trying to avoid. So first, we need to make sure that we split evenly A and B trials. Second, if you take any sequence of two trials, one nearby the other, you want to make sure that every A trial is equally preceded and then followed by the same number of A trials and the same number of B trials. Let me show you what I mean. If you consider any pair, you need to have exactly 1/4 of the time it has to be the sequence AB, 1/4 of the time it has to be the sequence BA, 1/4 of the time it has to be the sequence AA, and 1/4 of the time it has to be BB. So if you look at your experimental design and you look at the trials, it ought to be exactly 1/4 of the time the first sequence, exactly 1/4 of the time the second sequence, et cetera, et cetera. Not only, we can go up one level. And now every one of these pairs that you see here needs to have before it an equal number of time an A trial and an equal number of times a B trial. What does it mean? Well, it means that if you take any sequence of 3 trials in a row, 1/8 of the time it has to be AAB, 1/8 of the time it has to be BAB, 1/8 it would be ABA, 1/8 it would be BBA, et cetera, et cetera. In other words, we've taken each of these sequences, and half the time we precede them with an A, and half the time we precede them with a B. And then you can keep going. You can say, okay, so now let's take any 4 trials in a row. that also has to be systematic. So you take each of these sequences here, and half the time, so 1/16 of the time, before AAB, it would have to be AAB. 1/16 of the time, it would have to be BAAB, and so on and so forth. And you can see how this becomes pretty hard to implement in practice, because to fully counterbalance at all these levels, you need to have hundreds of trials. And hundreds of trials might sometimes be doable in fMRI, but sometimes it's not doable. If you're just presenting pictures of faces or houses, each of which takes 2 seconds to show, then you might be able to carefully counterbalance. But if you're doing some complicated task, maybe where each trial takes, who knows, 18 seconds, because it's a hard problem to solve, you might not have enough trials to do this full counterbalancing. So most of the times, currently what people do is actually they simply randomize the trials, which means every participant that undergoes the experiment just gets a different random order of these trials. So the sequence in which each individual trial happens is fully randomized across your individuals, which means that every individual gets a different random sequence. And it's very important that it be a different random sequence, because let's just assume that, just by chance, one of these sequences has some systematicity for it, just by chance. That could happen, but if it only happens in one participant, even if one participant happens to adopt some cognitive strategy, it might not be important when you're testing 20 participants and averaging your effect across 20 participants. Okay, so it's important that there not be any systematic strategy or cognitive set that all your participants or a majority of your participants adopt. Because if there is a majority of your participant that is using some strategy, that will show up in your group result. If it's only 1 or 2 out of a sample of 20, 30, then it doesn't quite matter as much. Worth pointing out that a lot of people use full randomization, which again means every single participant gets a fully random sequence of trials. Other times, people use what are known as pseudo randomizations, or constrained randomizations. For example, imagine that in your sequence of events, you also sometimes show the same. Let's say you're showing a number of faces and a number of houses. In order to have more trials, maybe you only have, let's say, 20 pictures of faces and 20 pictures of houses. Maybe in order to have more trials, you might show each individual face twice. So now, given one picture, you get 2 trials. You might want to constrain your randomization never to show the same picture back to back, right? Because that might create some kind of priming, right? So you might not want to do that. So you could put some kind of constraint on the randomization. Other times where you cannot fully randomize your stimuli, what people do is they take their series of trials and they create multiple randomizations. Maybe you create 5 different randomizations. And at that point, what you do is a subset of your participants sees, each of your participants sees one of these 5 randomizations. In fact, if you want to do it even better, you would create 5 randomizations, and then you would get some participants to see each of these 5 randomizations. Other participants would get the exact same randomizations, but in the reverse order. So now you're getting 10 randomizations where 5 of them are the opposite of the other 5. And there are many creative ways in order to do this if your design doesn't allow you to do a full randomization. If possible, full randomization, always better. But it might not always be possible. Your experiment might have some constraints. So you can use these other types of randomization in order to shuffle the trials sufficiently. Now, the second way that we have to tease apart events is not just to shuffle the trial order, but also to randomize the onset in time of your stimuli. What that means is that, for example, let's say you have a stimulus, instead of showing that stimulus, let's say every 3 seconds, so 3 seconds you show one stimulus, then you wait 1 second in between, and now you show another stimulus. Instead of keeping the spacing in between the stimulus, the so-called interstimulus interval, or ISI, instead of keeping that fixed, you randomly change the distance between your two stimuli. Effectively, what this will do, it'll do something similar to shuffling the order. It will move the distance in between stimuli, and this will allow you to tease apart overlapping trials, because sometimes they'll overlap and sometimes they won't. Let me give you an example. So what you're seeing here on the top part of this graphic is time on the x-axis and the signal change on the y-axis. Now, if you imagine having a number of trials and you put them 16 seconds apart, so the inter-trial interval is 16 seconds. You see here you get trial 1, then exactly 16 seconds later, trial 2, and trial 3, and trial 4, and trial 5. You can see the full response to each trial. And so it's easy to estimate, right? There's no overlap, and so it's easy to tell how much of the signal change comes from the first trial, how much from the second, etc. But now let's put them closer. Let's put the trials 3 seconds away from each other. What happens if you look at the bold signal is that it will increase, and then it will pretty much just sort of wiggle a little bit, but just stay up here until you stop, and then it would come down again. And see, there's no variance in here. It's hard for the algorithm, for the analysis, to tell, where trial 1 starts and where trial 2 starts. Even worse, if you put them 1 second away and don't shuffle, don't jitter, what happens is that you just get this big increase in the signal, and then it pretty much just stays there. And there's no variance in the signal that would allow you to tease apart what comes from one trial and what comes from the next one. Now compare that to, instead of having a fixed interval between the trials, we're now going to randomize. So trial 1 might be here, trial 2 might be here, trial 3 might happen out here. And so we're randomly changing the spacing in between two contiguous trials. Now, if you have 16 seconds in between trials and you randomize them, it doesn't matter, because you still get enough space in between trials that you can see each individual response. But look at what happens if you leave on average 3 seconds, but you randomly change it to be a little more or a little less. Now you get all this variance. Remember, we saw a shape that kind of looks like this one when we had 5 trials in a row in the yellow graphic that I showed you a few slides earlier. Right? So all this variance here allows the analysis to tease apart how much comes from A and how much comes from B. And even if you put them 1 second apart on average and then jitter randomly how close, if it's exactly a second, a little bit less, a little bit more, you still get a lot of variance, and the algorithm can use this variance to infer how much of a response came from trial A and how much of a response came from trial B. So the 2 main ways that we have to tease apart overlapping trials with overlapping bold response is to shuffle your events and to randomize or jitter their onsets in time. Now, you might wonder, well, but sometimes I can't shuffle my trial orders. For example, what if your task were to encode something, maybe read something, and then hold it in mind and then answer it? You cannot randomize the reading and the answering of the question, right? It's impossible. You need to first read a stimulus to then answer a question about it. So you can't randomize when condition A and condition B happen. So in those cases, what you do, you apply jittering. So instead of always saying, read something, then answer a question about it, what you do is you jitter the time in between them. And you randomly, sometimes they're 5 seconds away, sometimes 6, sometimes 7, sometimes 4. And as you do this, it allows the analysis to recover how much of a response comes from part A let's say the reading, the encoding, and how much comes from part B, the responding. So see, an example such as this shows how important it is, if you can't shuffle, to use jittering.